Hello, in this video we're going to look at the Nobel Prize in Chemistry in the year 1902, won by Emil Fischer for his work on sugar and purine synthesis. First we begin with some illustrations. Here you see the substances in question. You see here the purines. You see they're all part of a family, of course. They all have more or less the same structure. Here you can see it even better. A double ring with carbons and nitrogen atoms. These are sugars, glucose. We all know that this is a variation, as you can see. And here are even more variations on the sugar theme. We will come back to this later. Well, the lecture is held in 1902. I summarize it, sometimes using quotes, sometimes my own words. The chemical substances and processes in animals and plants have always fascinated chemists. Success was only achieved in the 19th century with Margrave, Lavoisier and Scheele, and only at the beginning of the 19th century organic chemistry became a new discipline, and it replaced animal and vegetable substances by many artificial products. It became an industry. It appropriated the fundamental problems of our science at the same time. Wöhler's famous synthesis of urea in 1828 was a starting point. But this area is now coming to a close. And now is 1902, of course. One-sided study of carbon compounds cannot suffice to elucidate the nature of chemical processes in other aspects. General chemistry has been diverted back into the path which it was following under the guidance of Berzelius, Gay-Lussac and Davy. Two examples, the purines and the carbohydrates. Purines is a generic term for a large class of nitrogenic organic compounds. We saw them in the beginning. The oldest member of the group is uric acid, discovered simultaneously by Scheele and Bergman. They were studied by Liebig, Wöhler, Strecker and von Baeyer, but without its chemical nature being ultimately determined. Closely related are substances occurring in the bodies of animals, like xanthine, hypoxanthine, adenine and guanine. Related are also three substances from the vegetable kingdom, caffeine, theobromine and theophylline. Needed was a systematic, synthetic treatment of the entire group. Today, chemistry is based on the concept of atoms and molecules. In the formula we just saw, C stands for carbon, H stands for hydrogen, N stands for hydrogen, N stands for hydrogen, and O stands for oxygen. And the lines is how the atoms are interlinked. All the pictured molecules contain a common atomic group, the purine nucleus. It consists of 5 carbon atoms and 4 nitrogen atoms, so arranged that the two cyclic groups with 2 common atoms are formed to be shown. Maybe we can look at that again. Here we are. 1, 2, 3, 4, 5 carbons, 4 nitrogens in 2 rings. And all the purines have that structure. To determine the structure, the system is broken down into components, what is called analysis. But usually the reverse method is used, building up the molecule from the decomposition product of similar substances, and that's called synthesis. It became possible to synthesize all purines from uric acid. Most synthesized is 3-chloropurine from uric acid and phosphoric chloride, replacing 3 oxygens with 3 chlorine atoms. The chlorine atoms can be replaced with other atoms or groups, creating new substances surpassing nature. 12 natural purines are known, and now already 146 new purines are synthesized. That is in 1902. Even more important, caffeine and theobromine are until now had to be extracted from tea or cacao. Now they can be synthesized from cheap uric acid on an industrial scale. Synthetic theophylline is already on the market, and theobromine and caffeine will soon follow. Since long many cheap coffee and tea substitutes were present on the market, but all lack the stimulating effect of the caffeine. Adding synthetic caffeine would help and also better the taste and the aroma. It's even possible to make real tea and coffee without leaves or beans. Same is true for dyes, coloring our garments and furnishing, and sweet saccharine. All are in the end derived from coal tar. The same is now becoming true for caffeine made from uric acid. Xanthine, hypoxanthine, adenine and guanine are constituents of the cell nucleus, the most important part of the living cell. To know their constitution will help physiology to follow their utilization in the cell. Also important for medicine, heretical is a mistake denk ik, patients with a tendency to uric acid diathesis can be cured by avoiding purines. An even more important class of organic compounds are carbohydrates. They are produced from carbon dioxide and they have been studied since the early beginnings of organic chemistry. Lavoisier did important work determining their composition. The progress was slow, the study gave specific problems and the systematology is complex since there are so many. Two important classes are named, the monosaccharides like grapefruit, glucose and the polysaccharides like cellulose and starch. Monosaccharides can fuse or dehydrate to form polysaccharides and polysaccharides can be split hydrolyzed into monosaccharides. Maybe you can go back to the to this group. You see these are all monosaccharides and they can be fused to form disaccharides or even more saccharides and you call it polysaccharides. Now 50 monosaccharides are known, 10 natural. With the very many different polysaccharides can be formed with these. 6 monosaccharide sugars are already known to exist in plants and sugars in animals. All these, in addition to a chain of 6 carbon atoms, it contains 5 alcohol groups and 1 aldehyde group. The structural formula is also valid for other sugars. 2 others are found to contain only 5 carbon atoms, such as arabinose and xylose. There's a picture of arabinose way back, you can look it up if you want. There have been in the past no lack of attempts to synthesize these compounds, but success remained extremely scant for only a single one of the many artificial products reported in other chemical literature and regarded as sugar-like substance had stood the critical test of modern methods of examination. Butlerov obtained from formaldehyde and lime water a sweet syrup containing almost no grape sugar. Grape sugar and glycerol both taste sweet, but are very different, and the syrup, of course, contained glycerol. Glycerol has only 3 carbons and has no aldehyde group. Sugar has 6 carbons, but it has polyvalent alcohol. Glycerol with dilute nitric acid changes to something sugar-like, glycerose. Scheele discovered glycerol 140 years ago. It now opens the gate to synthesis of sugars. Glycerol with strong nitric acid gives explosive nitroglycerin. Glycerol has a different composition as natural sugars. Under the action of dilute alkali, it undergoes polymerization. Lots of molecules together. 2 molecules together form acrose, a sugar with 6 carbon atoms. And after a small modification, it could be converted into grape sugar. Acrosa was also found in the earlier mentioned sweet syrup. Today it is even possible to make sugar starting from carbon dioxide. Synthesis goes further, making sugars with a higher carbon content. Sugars are able to fixate their aldehyde group hydrocyanic acid. When this is made to lose oxygen, it changes into sugar with 1 carbon atom more, thus 7. We can now make sugars with 8 or 9 carbon atoms. And what's a simple sugar? One with only 4 carbon atoms has been found. Still, this is 1902. The sugars are today described according to their carbon content by Greek numerals, to which is added ose. Now we go to isomorphism. Galactose and grape sugar have the same structure formula, but have different characteristics. The new theory, stereochemistry, studies models in spatial terms. Pasteur studies of tartaric acids was the beginning of stereochemistry. Pasteur found two versions of tartaric acid, one rotating light to the right and one to the left. He speculated that this was due to the asymmetrical structure of the molecule, and this proved to be right. This geometrical concept yielded result in 1874 when Nobel and Van Hoff attributed the asymmetry of the molecule to the individual carbon atom. In the sugar molecule, asymmetrical carbon atoms are present. Hexoses contains 4. Theoretically, 16 geometrically different substances of glucose were predicted theoretically, and 12 have already been found. Further on, you will see that formula. It's way back in the beginning of the film. The 4 asymmetrical carbon atoms have been left out and only intimated in the points of synthesis between the vertical lines and the 4 horizontal lines. Maybe we can go back to that picture of the. Here it is. You see? Okay. Here you see another one. This one has 5 carbon atoms. You see, this one has 6. It's already mentioned in the text. H and OH signify hydrogen and hydroxyl, then gives an idea of the geometrical arrangement of each asymmetrical carbon atom. Similar forma exists for pentoses and tetroses. The symmetry of the monosaccharides is complete. Maybe you come back again and you can see that all the monosaccharides here have hydrogen and hydroxyl groups, and you see that the place differs. Yeah? This makes them different substances, and they often have the same structural formula, but the place of the atoms can be switched. For instance, if you look at this one, you see glucose and glucose, but the place of the hydroxyl group here and here the hydrogen group is exactly the opposite on the other side. Yeah. Okay. I think we were here. Then something new. Glucuronic acid derived from glucose is used by animals to neutralize poison. Glucosamine is an intermediate between glucose and co-amino acid. It must be CC amino acids. One of the longest sought for bridges between carbohydrates and proteins. Glucosides found in plants are compounds of sugar with other substances. Examples: amygdalin and salicin. The problem to synthesize these are now overcome. It was discovered that there is no fundamental difference between glucosides and polysaccharides, so they may also be synthesized. This knowledge on synthesis can be used to solve biological problems. Enzymes are today very important chemical aids involved in most of chemical transformations in living cells. Their action depends on a geometrical molecule to be attacked. It must fit like lock and key. Maybe we can look at it. Here we have an example of a lock and key mechanism. Here you see the two fitting together, see you? Like a lock and a key. It's the same, but they're more complicated. The application of the new knowledge to the superb natural process without which the living world would not exist, for instance, assimilation of carbon dioxide from the atmosphere by plants, seems even more interesting. A difference to synthetic and natural sugar production. Nature only produces dextro-rotary sugars. Synthetic sugars are both dextro and levo-rotary. This was mentioned. Pasteur discovered that sugars can polarize right one way, clockwise or counterclockwise. Only one of them is found in nature, but in the laboratory both can be made. But now steps are taken to make synthesis of sugar just as asymmetrical. Nature has given us many of its secrets, but the chemical enigma of life will not be solved until organic chemistry has mastered another, even more difficult subject, the proteins, in the same way as it has mastered the carbohydrates. An enormous task. This is no longer work of an individual, but of groups. Well, this is the summary of the lecture. If you will read the complete lecture, you can go to the Nobel Prize site, nobelprize.org/prizes/chemistry/1902/Fischer/lecture. Okay, thank you for watching and maybe till next time.